Good morning, friends. Today we are discussing about module number 3, that is partial differential equation. An equation involving one or more partial derivatives of the function of two or more variables is called as partial differential equation. Equation involving one or more partial derivatives of a function of two or more variables is called as PDE. The order of PDE is a order of highest derivative, and the degree of PDE is degree of highest order derivative. So that we have example here: dou z upon dou x plus dou z upon dou y is equals to 0. Both carries first order and first degree. Here order is 2 but degree is 1. Here order is 3, degree is 1. Homogeneous, homogeneous, homogeneous. Linear. A PDE is said to be linear if it is of first degree in the dependent variable and its partial derivatives. Okay. Now we'll discuss about formation of PDE by eliminating arbitrary constants and as well as arbitrary functions. Given a relation of the form f of x, y, z, a, comma, b is equals to 0, where both x, y are variables, z is a function of x and y. Differentiating the given relation partially with respect to x and y, steps I am defining. Now we need to eliminate arbitrary constants a and b to form the PDE. The following standard notations when z is a function of two independent variables x, y will be used. So here we are using the notations: small p equals to dou z upon dou x, q equals to dou z upon dou y, r is equals to dou square z upon dou x square, t is equals to dou square z upon dou y square, and s is equals to dou square z upon dou x into dou y. These are the notations that we are using. Now we'll have examples. Formation of PDE by eliminating the arbitrary constants. First example, z equals to x plus a into y plus b. Differentiating partially with respect to x and y, we find out dou z upon dou x, because differentiation of x plus a with respect to x will be 1 and y plus b is a constant. I have treated y plus b as a constant, kept as it is. So y plus b into differentiation of x plus a will be 1. So we got y plus b and I have called p. Similarly, while differentiating z with respect to y, I have to treat x plus a as a constant, kept x plus a as a constant. Now differentiating with respect to y partially, we will get 1. So this is got x plus a. Okay. Now dou z upon dou x equal to p and dou z upon dou y equals to q. Using both, we'll get z equals to pq from the given equation. In the given equation, it is x plus a into y plus b. Substituting x plus a equals to q, y plus b equal to p. So we'll get z equal to pq is the required PDE, where it doesn't contain any constants like a and b. So arbitrary constants are eliminated. Now, second example, z equals to y square plus 2f into bracket 1 by x plus log y. So here we are finding PDE or forming the PDE by eliminating arbitrary functions, because f is a function of x and y. Differentiating partially with respect to x and y, we got first differentiating partially with respect to x, dou z upon dou x equals to p is equals to y square becomes 0, and differentiation of 2 into f is 2f dash of the same function. Again, 1 by x differentiation is minus 1 by x square. So we got dou z upon dou x equals to p equals to 2f dash plus 1 by x plus log y into bracket minus 1 by x square. Similarly, while differentiating with respect to y partially, differentiation of y square is 2y plus differentiation of f with respect to y is 2f dash. Again, log y is there, 1 by x is a constant, so I'm not interested. Let me differentiate log y. So we got 1 by y. So we got dou z upon dou x and dou z upon dou y. On cross multiplying for the equation, we got px square is equals to minus 2f dash into bracket 1 by x plus log y. Let me call it as equation number 1. Similarly, from this equation, I have taken 2y this side. So we got q minus 2y whole bracket into y after doing cross multiplication. Q minus 2y into bracket y is equals to 2f dash 1 by x plus log y. Concentrating on both the equation 1 and 2, RHS is same with respect to minus. So dividing 1 by 2, we got px square divided by q minus 2y into y is equals to minus 1. Okay. So after dividing equation 1 by 2, we got px square divided by q minus 2y into y is equals to minus 1. After doing cross multiplication, we may get the answer like this: px square is equals to minus qy plus 2y square. That is, px square plus qy is equals to 2y square. I have taken qy this side. It's a required PD where function is purely eliminated. So let's go through example number 3. It's phi of phi is a function. Phi of xy plus z square comma x plus y plus z is equals to 0. We have by data, and here I am using u as xy plus z square and v as x plus y plus z. It's immaterial. Here I have denoted u and v as a functions of x and y and z. If you are interested, you can use any other alphabets. Here I am interested with u and v, so I selected u and v. Now differentiating u with respect to x, I got dou u upon dou x. Differentiation of xy with respect to x will be y plus 2z square is a function of x. Z is not a variable, it is a function of x. So z square differentiation is 2z. Again, z differentiation is dou z upon dou x. And we have denoted dou z upon dou x as p. Similarly, dou v upon dou x we got. Dou v upon dou x will be 1 plus p because differentiation of x is 1, y is a constant which is 0, z is dou z upon dou x, I got 1 plus p. So dou u upon dou y means I'm differentiating partially with respect to y. X as it is, differentiation of y will be 1, so we got x plus differentiation of z square with respect to y will be 2z q because q is dou z upon dou y. Okay. Next, so we found ux, px, uy, vy based on the assumption that I'm going to solve this example by chain rule, by applying chain rule. So we have called phi of u comma v equal to 0 as 1. Let us differentiation equation 1 with respect to x and y by applying chain rule. So differentiation of phi with respect to u is dou phi upon dou u into dou u upon dou x plus dou phi upon dou v into dou v upon dou x is equals to 0 using chain rule, equating dou phi upon dou u into dou u upon dou x equals to minus dou phi upon dou v into dou v upon dou x. And I have called that as equation number 2. Now, with respect to y, dou phi upon dou u into dou u upon dou y plus dou phi upon dou v into dou v upon dou y equal to 0. So here, dou phi upon dou u into dou upon dou y equals to minus dou phi upon dou u into dou v upon dou x. Dividing 2 by 3, we obtain dou pi upon dou u and dou pi upon dou u get cancelled. This get cancelled, which is present in denominator as well as numerator. Okay, we left with dou u upon dou x divided by dou u upon dou y. Similarly here dou v upon dou x divided by dou v upon dou y. As we got dou u upon dou x, dou v upon dou y, dou u upon dou y, and dou v upon dou x. Substituting all these results in this equation, y plus 2zp divided by x plus 2zp, x plus 2zp is equals to 1 plus p divided by 1 plus q. On doing cross multiplication, 1 plus p into x plus 2z cube, 1 plus q into y plus 2zp. After multiplying x with respect to 1 and p, x plus 2zq plus xp plus 2zp, y plus 5q, 2zp, 2zpq. Here 2zp, 2zpq and 2zpq get cancelled, and concentrating on similar terms, I got x and y here. Taking y this side, I got x minus y. And concentrating on px, where p is a common term. Similarly here, 2zp, we got this. So on taking p common, I got x minus 2z on taking this side. Similarly, I got 2zq and qy. By taking q common, I got y minus 2z because I have selected this side. So finally, we got p into bracket x minus 2z minus q into bracket y minus 2z plus x minus y equal to 0 is the required PDE. Like this, we can obtain formation of PDE or form the PDE or obtain the PDE. It's not obtaining, it's forming the PDE by eliminating arbitrary constant as well as arbitrary function. So we have selected 3 examples. Please go through it and try to understand the examples. Thank you very much.